Okay, so we are on we're on 2.1. How far did we get yesterday? Example 3. We finished part A. Okay. So we're trying to determine if the following represent functions, yes or no. And we said yesterday on example 3A that this equation was or was not a function. It was not. Why? Y was squared. And remember, the exponent of the y typically means that's how many y values we have for each x. And to be a function, there could be no more than 1. 2 is bigger than 1, no good. The other way that we talked about it, if you're not sure about using that criteria, is to try to solve it explicitly for y. And remember, explicitly means you have y equals and no y's on that right side. So if I try to do that, I need to take the square root of both sides. We said yesterday, if you're the one introducing the square root, you have to consider what? Plus or minus. So you have the positive version, or you have the negative version. And by definition right there, that means for any given x, you're going to have how many y values? 2, the positive and the negative, okay, potentially. So not a function. B, function, yes, no, or maybe so? Yes. We have y to the first, we have y to the first, but there's 2 y's. And we said yesterday as the bell was ringing or not ringing, I can't remember what happened yesterday. It's always exciting. That those become 2y when you add them, not y squared. So we said that was good. Now the ultimate criteria, and I'm going to go ahead and do this, could we go ahead and solve that equation for y? Can we? Yes. We have 2 terms that have y in them. If I keep those like terms with the y in them on the left side, I could take the 4 that doesn't have a y to the other side. And then to solve for y, you would have to factor out the y from both of those terms. So let's do that. That'll leave me a 2x squared and a minus 8. Yes, yes? And on the other side, I have 7x, and joining him now is negative 4. And then to solve for y, how do I get rid of that 2x squared minus 8 factor? Divide. So I will end up with 7x minus 4 all over 2x squared minus 8. And that would end up being y equals, and are there any y's on the right side? I don't see any. So it's good. That would be explicitly solved for y. And so that's another way we can determine if it is a function. It is. We got it. Good. No, that's just another criteria. If we're going to be sketching it eventually, then we'd probably want to. But no, you don't have to. All right, what about this guy, girl, dude, thing? Function yes, function no. Let's see, I got a y to the first, that's okay. I got a y to the first, that's okay. I got a y to the 3 halves. Ooh, that's a fraction. Are all fractions less than 1? No. I only ate a fraction of a pizza. Really, what was the fraction? 15 halves. Wow, you ate a lot of pizza. Okay? 3 halves is bigger than 1, right? It's a 1.5. Now that means that for some x values, there's going to be more than one y value, right? Like 1.5. What does that look like? Half a y value? I'm not sure. But I know it's more than 1. More than 1. So what would you say? No. Okay? 3 halves is greater than 1. If you try to solve that for y, good luck. Good luck. I don't think you're going to be able to pull it off. I'm not doubting you. I don't think you can do it. I'm doubting you, I guess. Okay. All right. You getting the idea, right? All right, D, last one, and then we'll get on to something else. Last one before the next one. X equals the square root of y. Function, yes, no? Yes, because in disguise we can write the square root of y as y to the 1/2 power. And let's see, 1/2 is what in relation to 1? It's less than 1. Yeah, so this is yes. So 1/2 is less than 1. So for some x values, there's only going to be half of a y value. What the? How does that work? That's good. It's less than 1. Let's see what it looks like. To graph that, I'd probably want to solve for y, yes? Let's do that. How would I solve for y? I would have to raise both sides to the reciprocal of 1/2 power, which the reciprocal of 1/2 is 2. So I square both sides. And the reason that works is because 1/2 times 2 is what on the right? 1. If that was y to the 2/3 on the right, we'd have to raise both sides to the 3/2 power. You always raise it to the reciprocal power. That's why squaring a radical works. And then we get x squared. So if I flip that around, I get y equals x squared. Hey, it's our old friend. It's the old friend quadratic man. So let's see what that would look like. It would look like this, and then look like that. But do we see the whole graph based on what we started with? We always have to go back to what we started with. Notice that I could choose y value right here to be anything greater than or equal to 0. And that graph lives above and on the x-axis. But notice that when I take the square root, my x values are only going to be what types of numbers? Positive. So this is what the graph looks like. You don't see the negative part of the graph in x land. That's gone. That's what the graph looks like. It's the right side of the parabola. But is that still a function? Heck yeah. Yeah. Why is it only the right side? Because look up here in the beginning. Plug in any value of y that works, right? What type of x value you're going to get?
Well, when we solve for y, why does it trick us?
Well, we solve for y to try and graph it, but what we're going to be focusing on all this year is we always have to keep it in the context of the original equation that we're given. That basically tells us what the graph looks like. We only solved it for y as an aid to help ourselves sketch it, but then we always have to come back to the beginning. Like later on, when we look at domains, remember when we simplified expressions, like the x minus 2 factors might have divided out, and then we put comma, x can't be 2? Because we got rid of it, we need to warn people that, hey, in the beginning, x couldn't be 2. Same thing here. Okay? When you plug in any value of y, like a 2 or a 4 or a 9 or whatever, something easy, you're going to have x equals positive 2, positive 3. So they're only going to be positive x values, which are found in quadrant 1 or 4, but in this case, just 1. Okay, so it is a function. And you could, again, determine that from the original exponent being less than 1. Okay, so what we're going to do now is we're going to look at actual functions, and we're going to find the domains algebraically. We have some practice with that. Throughout the year, we're going to be doing this. Every time we meet a function, we're going to find its domain. So this is pretty important. There are essentially 3 things that we need to guard ourselves against, okay, in finding domains. We can't divide by 0, okay? So anytime we have a function that has a denominator, whether it's overt, okay, you actually see a horizontal line with x's below it, or it's covert. It's an expression written to a -1 power, or a -2 power, or what it is, negative power. That's a denominator in disguise. There might be x values that when you plug them in give you 0. We need to find those values and kick them out of the domain club, okay? The second thing that we've had experience with is we can't take the square root or the 4th root or the 6th root or any eventh root of a negative number. So we need to find the positive values in zeros. Those are the ones that are going to work. And then the negative numbers are off limits. Okay, and then the third one that we're going to be doing later in the year, not now, is we can only take the log of a non-positive, I'm sorry, I wrote that wrong. Oh yeah, taking the log. We don't want to take the log of a non-positive number. So we can only take logs of positive numbers. So later on when we have logs, when we study logs, we'll be finding their domains. But right now, we're going to limit ourselves just to these 2 cases. If you clear those 2 hurdles, then the domain is going to be everything that's left after you eliminate anything that causes division by 0 or anything that's going to be negative under an even root. Okay? Then the domain is everything else. Now it says eventh root. What about cube roots? Can we have negatives under cube roots, under 5th roots? Yes. If it's an odd root, then we can have negatives underneath it. Now just like a division by 0 can be in disguise by a negative exponent, roots can be in disguise by what type of exponents? Rational exponents, fractional exponents. Okay, so here we go. Example 4. Find the domain of each of the following and then state our answer in set or interval notation. There's a function. What's its name? F. Function F. Hello, F. Nice to meet you. I'm just going to kind of look around here and see if there's any contraband, anything off limits. Okay. If there's any x values that are going to do your harm, I will find them, and you'll be safe. Thank you, said F, if he could. Now, you look at the function, you're like, okay, does it have any radicals? Are there any square roots, fourth roots, or any fractional exponents? No. So we've already cleared that hurdle. Then we look to see if there's any denominators or negative exponents. You don't see do you see a denominator? There's a big denominator, right? Now, does the denominator have a variable in it? If the denominator was just like a 5, it's like, okay, 5, carry on. But we have variables, right? Ooh. So what does that mean? That means that there might be values of x that when I plug it in, when I square a number and add it to itself and subtract 6 from it, if it's 0, that's no good, right? So we need to find the values that potentially make the denominator 0. So it's like f of x, we're going to be in the basement, 3x, we'll try not to disturb you while you sleep. We'll be downstairs working. Here's what you do if you ever have a denominator. You say that the entire denominator, not part of the denominator, like we take part of the radical, just the radicand, the entire denominator, and we say that it cannot, shall not, will not equal 0. We're trying to avoid one number and one number only. There's only going to be, if any, a finite number of x values that will cause a 0. In this case, at most 2. It's a quadratic, okay? So we're going to find the values that do not work. We're going to find the values that don't work. It's a little bit easier to do that. If we can find the handful of values that don't work, then all the other ones should. So let's go ahead and do that. X squared plus x minus 6 does not equal 0. We're going to treat that like an equation. You can call it an unequation, a non-equation. I don't even know if it has a name. But we're going to treat it like an equation. So anytime we have an equation that's set equal to 0, what's our next plan? What's our strategy? What's our goal? What do we try to do next? Factor. You said factors? Sorry, didn't mean to start you. Factor. You were right. Factor. Factor, right? Factor. So let's do that. Hopefully it factors nicely, right? It does. X plus 3 times x minus 2. Now, you think it's important to bring down the not equal sign equaling 0, or can we just leave it like that? Oh, you better bring it down, right? Notation, notation, notation. Otherwise, it turns in from an unequation to an expression, and those are very different. Now, you can just look at those, hopefully, and get the correct answers. That means that x cannot equal what from the first factor? Negative 3 and then positive 2. Those are the only values that make the denominator 0. That's it. We've cleared the radical hurdle because there were none. We have identified the 2 guys that are going to cause problems. Now we'll throw them out of the club. So now we're ready to list the domain. So the domain sub f, d sub f, the function's name is f. It's the set of all x such that x is not negative 3, comma 2. And that's it. Those are the only 2 that don't work. And so when we do it in set notation, we'll assume that all the other what types of numbers do? Real numbers. All the other real numbers work. Good. And again, what about 3x on the top? Stays up there. It affects the graph, but it doesn't affect the domain. So we're done. We're leaving. We'll come out of the base. We'll say 3x. We're going to be on our way. Sorry to wake you. Okay? We're done. We're done here. Carry on. We've exterminated negative 3 and 2. Your roach problem is gone. Maybe it's a rat problem. Right? Oh? Feel sorry for the roaches? Ooh, 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 ooh. Oh. What's that? Up here? Right, we're not going to look at the third one anymore. We're going to be looking for any denominators with variables and any even roots with variables, and we're going to try and guard against those. We did not have a radical here, but we had a denominator. Okay? Well, up here I just listed that as number 1, division by 0. Okay? We don't want to divide by 0. So anytime we have a denominator, take the whole thing, say it can't be 0. All right, any other questions? If you didn't want to, exterminate the roaches, what would you do? Would you rescue them and send them to, a roach farm? Yeah? Okay.
How would you feel?
I don't know. They've been around since, before the dinosaurs, so, I mean, they can, oh, yeah. Really? I didn't know that. I do know that they smell bad when you step on them. Accidentally. Accidentally step on them. Oops, sorry, roach. Like when you're walking through the kitchen at night and you're barefoot, and you step and it's like, what was that? Was that a potato chip? Oh, no, potato chips don't smell like that. Unless that's a new Doritos flavor, in which case I'm not buying those anymore. Huh? Sour grape? Every once in a while. Yeah. All right. B, G of X. Not that we have a filthy house, but roaches, you know, they're just around sometimes. They can? You like roaches, I can tell. Anyway, that's good. They need people who like them. G of X, the function's name is G. Bless you. Do we have any square roots in here? Either covert or overt? Any in disguise? No, nothing. Do we have any denominators? Oh, yeah, we do. Does it have a variable in it? It does. You can probably look at that and see which value or values make the denominator 0 right away. What are they? 4. 4. Anything else? Oh, negative 4. Yeah. We got them. Now, in this case, this is pretty easy. I wouldn't really expect to see work on something like this because hopefully you do recognize that as a difference of squares. But if you want to show the work here, I would expect to see work over there. Let's just do it. We take the entire denominator. We say it cannot equal 0. And there's two ways to solve this. Since there's no x term, you can either extract the square roots by bringing the 16 across. And when you extract square roots, when you're the one introducing the radical into the problem, you're responsible for considering both what? Plus or minus the square root of 16, which is 4. Or, if you prefer, you can factor it. It's the difference of squares. And you can say that that can equal 0. And then you're probably less likely to miss the negative one. Because believe it or not, some people miss the negative one. They go in there to exterminate and they get the positive 4, but they leave the negative 4 around. And the negative 4 is the more sinister of the two. Right? So you leave like the big rat in the basement. We moved on to rats from roaches. I have never walked through the kitchen and I barefoot and stepped on a rat, just in case you're wondering. Okay? I would not like that. Scorpion, you know, we got scorpions too. Those, yeah, I don't like those either. Okay, what do we do with the 3x plus 12 in the numerator? Nothing. We don't want to be rude, so we should probably say, hi, numerator. Okay? But it doesn't affect the domain, right? Doesn't affect the domain. So, are we ready to express our final answer? Yeah, I'll box it up and I'm done, yes? No. No. That's not how we do that. We have to use the correct notation. So the set of all x such that domain, what's the name of this function? G? So D sub G, set of all x such that x is not, you can list it as plus or minus 4. That's fine. Okay, good. Now, what if this problem, instead of being written like that, was written as 3x plus 12 times x squared minus 16 to the negative first? And let's see if I can magically get rid of that. Let's see if there's a way. Can you highlight? Oh, it's still there, but you get the idea. I'm using white highlighter. Oh, it works better? Oh, okay. Oh, yeah, thank you. Oh, that'll work. There we go. We're going to get rid of the line, too. Sweet. What if it was like that? Would you just kind of walk up to the problem and say, looks like everything is good here, I'll be on my way? Or would you notice that there's a denominator in disguise? Yeah, that's like a basement in disguise. That's like a basement on the first floor. That's really, really in disguise. Okay? So if you have negative exponents, remember, that's a denominator in disguise. Okay? And then your first step would be to what? Probably rewrite it like that. Ta-da! Gosh, I love this notability. And then you can proceed the way we did. Got it? Yes? Okay, very good. So that was two that had domain restrictions that caused the denominator to be 0. Here we have h of x. Hello, h. You got any denominators? Trivial one, right? Whoa! That was... There we go. We have a trivial denominator. It's over 1. Is 1 ever 0? Even at Halloween? What if 1 went dressed as 0? Would that make a 1 a 0? No, it's still a 1 underneath. Right? The clothes don't make the man. So There is no variable in the denominator. Okay, that's the key. So we don't have to worry about division by 0. But there's one other thing we need to guard against, right? Square roots of negatives. No good. Now, because negatives are a whole type of number, not just 0, we're trying to avoid infinitely many negatives. Instead of finding the ones that don't work for radicals, of course, we find the ones that do work. And so our strategy has been to take the entire radicand, not the radical. Don't say the radical is greater than or equal to 0. That's very, very different. You say the entire thing underneath it has to be greater than or equal to 0. And we're going to find the ones that work. We're going to find the x values that actually work, not the ones that don't work. So a little bit different strategy. You're used to this though, right? Once you say that it's greater than or equal to 0, it being the radicand, we carefully solve this linear inequality, and we get x is greater than or equal to 3/2. Now, do we just box it up and walk away, or do we check it first? We check it. Something bigger than 3/2 that we claim will work, like 2. 2 times 2 is 4. 4 minus 3 is 1. Yeah. Something that's not bigger than 3/2 that we claim will not work. 1/2. Okay. 1/2 times 2 is 1. 1 minus 3 is negative. Who cares? It's a negative. It doesn't work. That means we got it. So now we write our domain. The domain of H is the set of all x such that x is greater than or equal to 3/2. Plug in any of those values, and you're going to get a positive number or 0 under the radical. That's pretty easy. That's review. Questions on that? What about the +1 out there? Yeah. Yeah. All right, P of x equals 4 minus, okay, same thing, right? 4 minus 7 on the outside. They do affect the graph, but do they affect the domain? No, we got a square root. Over here, of course, before I go on the next one, if that was 2x plus 3 to the 1/2 plus 1, you would still spot the radical, yes? Yes, okay. And your first step would be to probably rewrite it. Okay, this one here, we do have a radical, no denominator with the variable, so we say that 3 minus 5x is greater than or equal to 0. And whenever you have the negative x, these are the ones you have to be extra careful on, right? Extra careful. These have teeth. Roaches with teeth. Oh, my goodness. When you bring the 3 across, it becomes what kind of 3? -3. That's the first mistake that a lot of people make. They're in a hurry. They bring the 3 across. They don't change the sign. Okay? You bring something across, the sign always changes. Now, here's the other common mistake. You're in a hurry or whatever, and you divide or multiply by negative, and you forget to do what? Flip the inequality. We're not going to forget. -3, -5 is +3, +5. And then we always get in the habit of checking, right? To catch any one of those two potential mistakes. If it was -3/5 or you forgot to flip it, we can catch it. Something less than 3/5 we claim will work, like 0. I like 0. Plug in a 0. 3 minus 0 is 3. That works. Yay. Something that is not less than or equal to 3/5, like 1, should not work. 3 minus 5 is negative. Who cares? Doesn't work. Negative under a radical. We got it. We're ready to express our domain, right? Yes, okay. The domain of P is, let's do interval this time. What the heck? You can do set. Yeah, keep it. Well, what is it going to be? Interval notation. Parentheses, -infinity, 3/5, bracket. Yeah. I don't care which one you use. As long as it's correct, it's good, and you have the right notation. Okay, so those are pretty easy. The next set of examples, getting fun. Getting really fun now. Fun with functions, yeah. Here's the deal. Sometimes you have roaches and rats. Spiders? I like spiders. Don't mess with my spiders. Don't mess with spiders. What I mean by roaches and rats are your two favorite varmints to hate. You have radicals and denominators in the same function. So you have to potentially look at both things in one problem. That's fun. So notice this problem here. It's y equals. So it doesn't have a function name. How do we know that's still a function even though it's what? Y to the first, and it's explicitly solved for y. There's no y's on the right side. Okay? So we have a radical in the numerator with a variable underneath it, and it's the square root, and we have variables in the denominator. So we have the possibility of both things happening. Which one should we do first? You should do the radical first. Okay, you probably don't know, so I'll tell you. There's really no specific order, but I would do the radical first, or the radicand first, whatever you're going to call it, because the radical is going to eliminate infinitely many values, right, because we're trying to avoid negatives. Okay, whereas the denominator only excludes, at max in this case, 2. Do the radical first because it gives you the chunk of your numerator, or of your domain. So, how do we do that? For the radical, we take the radicand, just the radicand, and we say it's greater than or equal to 0. So we quickly solve that, but not so quickly that we mess up, and we get x is greater than or equal to 1/2. We quickly check something bigger than 1/2 we're going to say is going to work, like 1. You get 2 minus 1 is 1, square root of 1 is 1, it works. Something not bigger than 1/2 that we say is not going to work, like 0. Try 0. You get 0 minus 1, that's the square root of negative 1, that's imaginary, doesn't work. Okay, so we got it. I'm just doing that quickly because that's how fast you do it in your head, right, without me to slow you down with all the words. It doesn't take long to check, but some people still aren't doing it, okay? Just check. Well, that's not our total domain right now, so I'm not going to formalize that with the notation. That is the demands of the radical. It's like you have two parties here. You have the radical, and they're making a demand. I have to be bigger than or equal to 1/2. All right. Calm down. There's another party involved, okay? We now need to go see the demands of the denominator. So we'll do the denominator second. Now, how do we do the denominator? We take part of the denominator, our favorite part of the denominator, or all of it? All of it, x squared minus 3x minus 10, and we say that it cannot, shall not, will not be 0. And now we solve this like an equation. So we try to factor it, right? X minus 5 plus 2. Man, we're so lucky these factor so easily. So x shall not, cannot be 5, and x shall not, cannot be negative 2. So what we have to do now is we have to combine the results. The radicand says, I must be greater than or equal to 1/2. And the denominator says, I ain't going to be a 5 or negative 2. Make sure that don't happen. Doesn't happen, denominator. Doesn't happen. Used in proper grammar. All right. So you could be kind of like an amateur compromiser, and you could say, okay, the domain, you don't have to put sub f or sub g because it's just y. It's the set of all x such that x is greater than or equal to 1/2. That's the demands of the radical. And then, of course, x cannot equal 5, and x cannot equal negative 2. And you're not saying anything wrong. But you're kind of being silly. You're repeating things, okay? Because what you're kind of doing is you're making the statement like, I like peas and carrots, but I don't like peas, even if they're with carrots. That just doesn't make sense, right? Because here's what we're saying. X has to be greater than or equal to 1/2. But x can't be 5 or negative 2. Okay? We've said something twice, right? This is why we do the radical first. We have already essentially excluded the negative 2 part from the demands of the radical, right? So when the radical says, I have to be greater than or equal to 1/2, and the denominator says, I can't be negative 2, it's like, all right, we won't have a problem then. If you're going to put that in there, it's not going to be wrong. But then what's going to prevent you from saying then, well, x can't be negative 7 or 5 or negative 11. You can start adding all those things in there unnecessarily. You don't need that because you got the inequality. So what I want you to try to do then is to be efficient. So we're going to get rid of that. We don't need that in there. We have already essentially said that from the radical. So here's the deal. If you get in the habit of doing the radical first, you're going to get the chunk of your domain. You would then only need to exclude the values that cause the denominator 0 that happen to be in the range of that inequality. What's that? If they both were greater than 1/2, we would exclude them both. Sometimes you might have none of them being greater than 1/2, and then they're already omitted, okay? Questions on that? That was kind of a double duty thing there. Bless you. I would like to start another problem, but guess what? I think we're going to be out of time. Yeah. So The worksheet awaits. You kind of have the seeds of greatness within you already to master the entire worksheet. So I would definitely take a look at it and start doing some of those problems. The key is online. We'll have these types of questions, of course, on the test on Tuesday, in addition to problems from the previous test from 1.1 and 1.2. Okay? We will probably make the worksheet due on Tuesday. I need to look at it and see how far we get. I don't think we're going to finish, so it might be one of those exceptional things like last time where it's due afterwards. This has been a crazy 6 weeks. Okay? It's been essentially 4 weeks in one day.